Greetings, it's Paul Bamberg with the introductory video for Class 8 of Math 117. You should watch this before coming to class on September 27th. Topic is independence and random variables. First, I will define what independent events are. If we've got two events A and B in some sigma field, we say that they're independent if the probability that they both happen, the probability of the intersection A intersect B, is equal to the product of the probabilities for A and B. Just knowing the sigma field doesn't let you decide in general whether events are independent. You have to know the probabilities assigned to them. A word of warning: it's easy to confuse independent with disjoint, but the two concepts could scarcely be more different. Events A and B are disjoint if at most one of them can happen, in which case knowing that one of them has happened automatically tells you that the other did not happen. Disjoint events are about as far from independent as it can get, and in fact the only way two disjoint events can be independent is if one of them has probability 0. Having defined independence, I can now move on to conditional probability. The conditional probability of B given A, written probability of B vertical bar A, is defined to be the probability that both A and B happen divided by the probability of A. If the events are independent, then the probability of the intersection A intersect B is the product of P of A and P of B. That's what independence means. So for independent events, the probability of B conditioned on A is just the same as the probability of B. P of A appears in the denominator in the definition of conditional probability. That ought to lead you to worry a little bit. And the remedy is this: you are never allowed to condition on an event whose probability is 0, even if that event is something like the probability that you will throw heads forever when you flip a coin an infinite number of times. You can't condition on an event of probability 0, even though that event may not be, strictly speaking, impossible. There are two ways of looking at conditional probability on a smaller set. The first one is done on page 91 in Dineen. Pick any event whose probability is greater than 0, and you can make a new probability space without changing either the sample space or the sigma field by just using the probability conditioned on A as your probability function. Dineen proves this in a few lines, pointing out, for example, that if you have an event B in the sigma field, not necessarily a subset of event A, the probability of A intersect B cannot be greater than the probability of A, so the probability function can't give you a value greater than 1. There's another view of this situation that I slightly prefer. You can say, I'm going to regard the event A, a subset of the sample space, as a new smaller sample space in its own right. Then as my new sigma field, I will just take the intersection of everything in the sigma field with the event A, and again I'll use probabilities conditioned on A as the new probability function. This approach frequently works very, very well in cases where you have a finite sample space with all points having equal probability, and you say, I'm going to confine my attention entirely to the sample space represented by event A. We can talk about independence for sigma fields. Suppose we've got sigma fields F1 and F2. They are independent if every event in the first one is independent of every event in the second one, and the perpendicular symbol is used for this concept. If, as is frequently the case, F1 and F2 are each generated by a countable partition, is that each event A sub n in the first partition has to be independent of each event B sub m in the second partition. When two sigma fields are independent, what it means is that information about which event in the first of these fields has happened provides no information about whether or not some event in the second sigma field has happened. Usually these events correspond to what people like to think of as independent experiments. Let's try being a little bit more formal about the concept of a compound experiment. For example, an experiment where you first roll a die and then flip a coin. People are fond of saying that these experiments are independent because clearly what happens in the die roll doesn't influence the outcome of the coin toss or vice versa. But our definition of independent events means we have to talk about two events from the same sample space. We can't talk about the die roll as coming from a sample space with 6 points in it. The coin toss is coming from a sample space with 2 points in it. Here's the way Dineen deals with this issue. The notation looks a bit complicated, but it's actually a very straightforward idea. Omega 1 is the sample space for the first experiment, the die roll, omega 2 for the second experiment, and the sample space for the compound experiment is a Cartesian product. Its elements are pairs, where the first element in the pair is the number on the die, and the second is either H for heads or T for tails. Now let's look at a couple of events. The event A2 involves only the die roll. It's the union of 2 combined with a head and 2 combined with a tail. The event B sub H doesn't involve the die roll at all. It's the union of the 6 events where you get the 6 possible numbers on the die, but the coin comes up heads. These are 2 events in the same sample space. They have the property that the probability of their intersection, which is 1/12, is the product of their probabilities. The first event has a probability of 1/6, the second of 1/2. If we want to be a bit fancier about this, we can introduce a couple of projection operators. Pi1 takes one of these pairs and extracts the first element, namely the die roll 2. Pi2 extracts the result of the coin toss, which is the tail. And now we can use inverse images to construct the required event. The inverse image of 2 is the event A2. That's the 2 combined with either tail or head. And more generally, the inverse image of Pi1 for event A is the Cartesian product of the event A with everything in sample space 2. Similarly, the inverse image of H under Pi2 is B sub H, all the events where the coin comes up heads. And there is a little typo in here. That should have been a 2. Sorry about that. The inverse image of B quite generally is the Cartesian product of the sample space omega 1 with the event B. If we want a probability measure on this product space, all we have to do in the case of independent events is take products of probabilities. If you like, you could even draw yourself a nice little 6x2 grid to illustrate this situation. Now I can define a random variable. A random variable is not a variable, it's a function. It's a function on a probability space, and the important property of a random variable is it has to be a measurable function. all that you've learned about measurable functions will carry over to random variables. So, for example, the sum of two random variables is a random variable because they're measurable functions. If you have a sequence of random variables, the limit is another random variable. Or if you take a function of a random variable, as long as it's Borel measurable, and remember, it's very, very difficult to invent a function that isn't Borel measurable. That Borel measurable function is another random variable. A measurable function, as you'll recall, generates a sigma field. A random variable does more than that. It generates a probability space. Now this is a probability space where the sample space is the real numbers, and the sigma field is always the collection of acceptable subsets of the real numbers. The Borel sigma field where we have excluded strange things like Vitali sets. The probability measure that works for this probability space is defined by saying that the probability measure P sub x applied to some Borel set B is the probability of x inverse of B, the probability of the event in the sample space that leads to a real number that lies in the Borel set B. If we think about dartboards, it's obvious to see what's going on here. So the random variable x is the score on a dartboard. The open interval from 4 to 21 is a subset of the real numbers, a Borel set, and this is the probability that the dart hits in a region of the board where the resulting score is greater than 4 and less than 21. What makes life tricky is it's entirely possible to have different random variables on different sample spaces and end up with exactly the same probability measure P sub x of B. And in fact, if you look at what's done in standard probability courses, the overwhelming majority of the time is devoted to studying such functions. You look at an introductory course in mathematical statistics, say, and you get the idea the sample space is always the real numbers. Here's an illustration of this phenomenon of identically distributed random variables. First experiment, we roll a single fair die, and the random variable is the indicator function for a 6. So it equals 1 if we roll a 6, 0 otherwise. Assuming the die is fair, the probability is going to be 1/6 for any Borel set that includes 1 but not 0, and it is going to be 5/6 for any Borel set that includes 0 but not 1. That takes a bit of thinking about. If I say, what's the probability that x lies in the Borel set from 0.5 to 10, the answer is that includes 1, and you get a 1 by rolling a 6. The probability is 1/6. Okay. Here's a second example with a different experiment. The event is you roll 2 dice and the sum is 7, and the random variable in this case, which I will call y, is the indicator function for that event. Again, if you pick any Borel set that includes 1 but not 0, the probability of getting a value in that Borel set is 1/6. It's 5/6 for a Borel set that includes 0. A third example, we got a horse race. Dineen's Pride is running with odds of 5 to 1, and the event in this case is W. Dineen's Pride wins the race. The random variable is the indicator function for that event. Yet again, the probability function for a Borel set that includes 1 but not 0 is 1/6, And so we've seen 3 different experiments, 3 different random variables, but the probability function is the same for x, y, and z. The technical term for this is that these 3 random variables are identically distributed. Now, you remember that a measurable function generates a sigma field. Suppose we have measurable functions x and y. They generate sigma fields f sub x and f sub y. And if these measurable functions are random variables, we can ask the question, are these sigma fields independent? If they are, then we call the random variables independent. Remember that independence is defined as a property of events. The probability of A intersect B is the probability of A times the probability of B. And we can recast this idea of independence in terms of events. Suppose we have 2 different Borel sets. Remember, these are subsets of the real numbers A and B. Then we can construct 2 inverse images, subsets of the sample space, x inverse of A, which gives rise to A, and y inverse of B, which gives rise to B. If, as random variables, x and y are independent, then the 2 events in sample space, x inverse of A and y inverse of B, are independent, and the converse is also true. Now you can invent situations where events are independent without regard to probability, where you don't need to know probabilities in order to conclude that 2 events are independent. Here's a particularly simple example. You're rolling a red die and a green die. The sample space is the Cartesian product of the numbers 1 through 6 for the red die and for the green die. We can define 2 random variables on this space. The first one, x, is obtained by dividing the number on the red die by 3 and keeping the remainder. The second one is the quotient in the 4th grade sense of quotient and remainder when you divide the number on the green die by 2. So, for example, if the green die shows a 3, the value of random variable y will be 1. Now, since one of these events involves only the red die and one involves only the green die, you'd say, yep, these events look pretty independent to me, and indeed they are independent whether or not the dice are loaded. Let's invent a couple of Borel sets to deal with this. The first Borel set, A, consists of the numbers 0 and 1, while the Borel set B is the open interval from 1.7 to 6.2. What's x inverse of A? Well, it's anything that gives a remainder of 0 or 1 when you divide by 3, so that gives 1, 3, 4, and 6. What's y inverse of B? It's anything that gives a value between 1.7 and 6.2 when you roll the green die. That means we have 4, 5, and 6, because those are the numbers where the quotient is going to be 2 or 3. Whether or not the dice are loaded, these are going to be 2 independent events. Finally, we can come up with a useful test for independence. This is proved in Dineen, it's Proposition 5.19. Remember that if you pick any Borel measurable function f, this is a function whose domain and codomain are the real numbers, and apply f to a random variable x, the resulting function is measurable, and you get a sigma field that is a subset of f sub x. Now, if you have an infinite sample space, it's perfectly easy to come up with random variables that are not necessarily bounded. I had a roommate who had a tough time with the Harvard language requirement. He tried to meet it in German and eventually succeeded on some attempt, but if you define a random variable to be the number of times that he has to take the Harvard placement test in German before meeting the requirement, that is an unbounded random variable. There's no guarantee that even after 37 attempts, my roommate would pass this test. Now, it's going to turn out that bounded random variables are much easier to deal with than unbounded ones, and a quick and dirty way of turning an unbounded random variable into a bounded one is simply to apply a bounded function f. For example, a function f that takes any real number, leaves it alone if it's less than 17, turns it into 17 if it's greater than or equal to 17. One way of testing for independence of two random variables x and y is that if you apply any bounded functions, the resulting random variables are also independent. And you can make a simple example of this. For our dice example, you could let f of x be the indicator function for 1, 3, 4, and 6. Those were the important numbers on the red die. G of y is the indicator function for 4, 5, and 6. Those were the valid numbers on the green die. These indicator functions are independent random variables, and therefore those events from the preceding page, remember those were defined in terms of Borel sets, are also independent events. So that's independence, and that's the end of this video.